Good evening, everyone. My name is Megan Neer, and I am pleased to welcome you to the Community Science and Technology Seminar Series presented to you by Pacific Northwest National Laboratory. This seminar series is intended to introduce you to the world-class research and development that's taking place right here in your community for 55 years. And normally we hold these in person, but given the current unfortunate COVID-19 situation, we've modified the format and we hope that you enjoy this virtual seminar. We do expect to have one virtual seminar per month from here on out for the foreseeable future. More information and registration for webinars can be found on the PNNL events page, which is pnnl.gov/events. Did want to let you know that we are planning a COVID-focused special series to run all 5 Tuesdays in March. Information for those webinars has not been published yet, but again, keep an eye out on pnnl.gov/events for more information on those. Now, I'd like to start tonight by doing a quick poll. If you turn your attention to your screen, you should see a poll pop up. We're just interested in knowing where you're logging in from. We've gone virtual with this, so it's nice to see if we've got people from outside of the area. And if you don't see your region on the poll, please drop us a line in the chat window. Be happy to give you a shout out there. We've got a lot of people from the Tri-Cities area and quite a few from other. Portland, DC, Philadelphia, Florida, Boise. That's great. Thank you. And then we also would like to know a little bit more about the demographic of our attendees. So what best describes the stage of your career? I think we've got most of the options out there for you, and we've got a nice mix of people calling in today. Great. Thank you for your feedback. So at the end of tonight's talk, it would be greatly appreciated if you could take our brief survey. Looks like Cassie put the link in the chat window, so you can copy and paste it from there into the browser of your choice. And for your convenience, we'll display and share the link again at the end of tonight's talk. We really appreciate you taking time to give us your feedback because we want to make sure that you see value in these seminars, and we'll make improvements based on that feedback. This is also your opportunity to sign up to receive emails from us about upcoming seminars, including the special COVID series taking place in March. So before you learn about tonight's topic, your presenter is going to give you just a brief overview of the National Laboratory System and PNNL's missions. You will also learn more about Battelle, the operator of PNNL since 1965 and the Tri-Cities' largest employer, and its staff and how they take pride in being excellent community stewards through philanthropy and volunteering. Now let me introduce tonight's presentation and speaker so we can get started. Tonight's presentation is Inspired by Nature, Learning from and Mimicking Nature in Materials and Chemistry. And your presenter is Wendy Shaw. Dr. Wendy Shaw is a biophysical chemist and a division director here at PNNL. She learns from nature to understand how bones and teeth are made and also how enzymes work to ultimately enable improved materials and renewable energy by mimicking the superior processes found in nature. Welcome, Wendy.
Thank you, Megan. Let me get my talk set up here. Ooh. I forgot the detail. All right, and I'd like to thank all of you for coming and attending my talk today. I'm really excited to share with you about how I'm inspired by nature. I'll start with just some details about me. So I grew up in Kettle Falls, Washington, which is up near the Canadian border. I then moved to WSU to go to undergraduate school, spent a year and a half there, but finished my undergraduate degree at Whitman College in Walla Walla. I then got a job at PNNL and worked at PNNL for about 3 years before I decided I wanted to get a PhD. So I went to Seattle, went to University of Washington, got a PhD in biophysical chemistry, and then came back to PNNL. So I've been kind of bumping around Washington State doing really cool science for a long time. I have 2 science areas. One is in biomineralization. I'm going to talk about that today a bit. And that's really about your hard tissues, like your bones and your teeth, and how those form. I also have an area of research in understanding catalysts to enable renewable energies. And I won't have time to talk about that today, but maybe I'll have an opportunity sometime in the future. And just to round out the picture, I thought I'd share some of my hobbies. I have too many. They wouldn't all fit here, but this is a nice sampling, but definitely the inspired by nature theme extends itself from my science into my personal life. One of the things I'll point out here is that my husband and I have horses, and they're going to be part of my talk today. Before I get started on my talk, I wanted to talk about PNNL and the national labs. In my mind, the national labs are a gem of the United States, equivalent to the national parks in their boldness and vision. They bring together some fantastic scientists to solve really hard problems for the United States, including things around energy security, national security, and environmental management. And it's just a really fun environment to work to solve these really important missions. One of the other things that we do is to focus on fundamental science, which is science that develops concepts in chemistry and physics and biology and other areas that don't have a specific application right now, but could be applied to those technologies that we use from day to day. And so that's a lot of fun too, to developing those next generation ideas that can help to move forward our technologies. There are about 5,000 employees at PNNL and about $1 billion of business. Inventions are really important to our work, as well as patents. And we also have quite a few companies that have roots at PNNL. And of course, the people are what make PNNL so special. There's so many activities that the staff at PNNL contribute to make our community better. Things from judging at science fairs and science bowls, to Habitat for Humanity, to collecting coats for kids. So it really is fun to have such a dedicated group of people to work with that care so much about science as well as the community. And so with that, let's find out why I'm inspired by nature. So nature is really inspiring, whether it's a mountain lake or a Mediterranean coastline, a national park, a savanna in Africa, or even an atoll in the South Pacific. We go to these places to find ourselves, to lose ourselves, sometimes to challenge ourselves. We go there for quiet and reflection, and we really are inspired by all of these things, many people as well as myself. I won't be talking about this kind of nature today, so I won't be offended if you thought it was about this and you prefer to sign off. That would be just fine. What I'm going to talk about today, I call this big nature. What I'm going to talk about today is what I call little nature. Very technical term, little nature. What do I mean by that? Well, if you think about a shell, they have these beautiful structures that are really difficult to make in the lab, and it's controlled by atomic level interactions and molecular level interactions. I show here something that's called an enzyme that could help enable renewable energy if we could implement it in the right way. Butterflies' wings are colored not just by their pigment, but also by a quality called iridescence that's created from a bunch of prisms that are in its wings. Neurons and synapses are sending thousands of messages through our body, controlling everything that we do second to second. This is a very beautiful structure that's highly controlled and orchestrated that can concentrate CO2, that if we could understand how to implement this in the right way, could potentially take greenhouse gases and convert them to something useful. Geckos, who wouldn't want to walk on a ceiling, right? And then teeth. I'll talk about those a bit more today, but teeth are, we see the structure that we have, but it's controlled at an atomic and a molecular level. And this is what I mean by little nature. And many scientists are inspired by little nature. And so I want to talk for a minute about bioinspiration. What does that mean exactly? Well, I mentioned I had horses, and so I'm going to talk about a horse example. And so in 1702, a man named Thomas Savery made a comparison between steam engines and horses. And basically, he had said something like this: if you can take 2 horses and run them, pull enough water up, and then take 2 more horses and 2 more horses, because they can't work all the time. So in the end, you'd have 10 or 12 or 14 horses to move this water. And if you could run a steam engine more cost effectively than it takes to manage and take care of those horses, then you should use a steam engine. And so the steam engine was one of the first opportunities that there was to directly compare the power of a horse to something man-made. And so these are two of my guys. This is Rolex and Blitzen. And they're not draft horses. They're kind of little. They probably aren't really a full horsepower, but we're going to call them that just so they don't feel bad. What's really cool about power is that anything that generates power is still compared to units of horses. So you look at an average car, 130 to 200 horsepower. You look at an aircraft carrier, 260,000 horsepower, and a space shuttle, 37 million horsepower, still compared in units of horses. A lot of scientists will tell you that if you take Rolex and 37 million of his friends and strap them to the space shuttle, you are not going to end up at the moon. And I got to say, a lot of horse trainers are going to tell you the same thing. So this isn't going to happen, right? And our intuition tells us that. But being inspired by biology is taking the power of a horse, first comparing that to a steam engine, then making a leap from a steam engine to a different kind of engine, a jet engine, and then having the inspiration to learn how to fly from a bird, putting those things together and doing something that we don't see in nature, which is going outside of our atmosphere and out into outer space. And there are quantum leaps that are needed there, but being inspired by biology is to take a concept that we see in nature and use that for our own purposes. And so this is something that just is very exciting to me. Okay, so I showed you a bunch of things that I describe as little nature. And the work that I'm showing just in these pictures isn't the full breadth of little nature, but it on its own represents thousands and thousands of researchers that try to understand this. So I won't cover all of this today. That would simply be impossible. As an example, I saw talk the other day on neuromorphic computing that tries to mimic neurons and synapses in the body. It looked really cool. I don't know anything about it. Won't talk about that today. I do have an area of research looking at catalysts and trying to enable renewable energies, but I won't have time to talk about that today either. What I'm going to focus on today is materials that are used in the body and both the positive effects of the pad and the things that we still have to learn. And so I'm going to start in prehistory. So bio-inspired materials have been used in the human body for a very, very long time. Things like gold, iron, and nacre are things that were used to replace teeth. Sutures were included animal intestine and linen, and prosthetic limbs have been very common throughout history. We didn't reach a really intentional use of bio-inspired materials in the body until World War II and just beyond that. And there were two very specific reasons for that. The first is captured in the picture on the right-hand side of the screen, where in World War II, there were these ball turret gunners that were on B-17s amongst other planes. And these gunners would sit inside the ball turret that you can see on your screen, and they would shoot at the enemy, and the enemy would shoot back. And these windows that you can see right here are made of a plastic called polymethyl methacrylate. We call that PMMA. After World War II, what surgeons were finding is that this material, when that material shattered, sometimes it would go into these gunners' eyes. And what was interesting is that it was just sitting there. It wasn't infected. It wasn't, there was nothing wrong with it. The body seemed to be okay with it being there. It was just sitting there, which is an improvement over many times when a foreign substance goes into the body. There's an immune response reaction that can be very violent to the point of killing the patient or the subject. And so it was very interesting to surgeons that these were just sitting there, basically being accepted by the body. Sir Harold Ridley did the first intraocular lens. This is a lens you replace if you have a cataract. He did this operation, I believe, in 1949. And so this was the start of an intentional implementation and placement of foreign materials in the body. The second thing that happened in World War II is that surgeons during the war really had carte blanche to do whatever they needed to do to try and save lives. And so they were really creative. They used parachute cloth for vascular grafts. They used sausage casings for kidney dialysis. And so this advanced the field much more quickly than might have been done in times where that desperation of trying to save a life wasn't driving effectively the science. So today, many different materials are used in the body. We talked about intraocular lenses. Knee and hip replacements are very common, about 300,000 a year or more, and titanium and stainless steel are common materials there. Catheters, there are over 1 million catheters a year. Silicones are a very common material, and vascular grafts are also very common, Gore-Tex being one of the common materials there. And so these have done so many good things to improve our quality of life. They've made many people more mobile when they wouldn't have been able to move around. They allow people to see or see better. They are literally life-saving in terms of catheters. And so they've improved our quality of life in so many ways. However, we all know stories of places where they haven't really lived up to what we want them to. For instance, knees and hips typically have a lifetime of 15 to 20 years, and so they have to be replaced. The reoperation of intraocular lenses is quite high. Catheters fail, heart valves calcify. And so it's pretty clear that while we're able to, at some level, work with biology, we don't fully understand what biology needs us to do in the human body to make these totally successful, where they fail or they cause a lot of pain to the people that have these materials. And so this is your opportunity to participate. I'm going to have several polls, so keep your keyboards close. But the first poll is right here, and I'm going to launch the question. And the question is, do these materials that I'm showing on the screen here all have similar properties? Yes or no? I'll give everyone a second to answer. I'd sing the Jeopardy theme song while we're waiting, but I don't really think you'd want me to do that. A few more still coming in. Last call. Okay, I'm going to end the polling. So we have, I'll share the results. We have 68% no, 32% yes. We've got a smart crowd today, guys. Yeah, these things are not the same. We have plastics, we have metals, we have soft materials, we have hard materials. These things are very, very different. But here's the really interesting thing. And so these are just to show that these do have different properties. Really interesting thing though, you stick these in the human body, they look exactly the same to the human body. And here's what happens. Proteins come down, they bind to the surface, and it encapsulates this material, walls it off from the body. It's interesting because it's totally uncontrolled, non-specific protein interaction. I'll talk about proteins in a minute, but nature never uses this. Nature is extremely specific about everything that it does. And so it's really all the body's doing is it's seeing it, it's saying, I don't want it there, so I'm going to wall it off. And currently, this is the benchmark for success. I think of this a little bit like having a rattlesnake in a terrarium in your house. If it's in the terrarium, can't get out, you're confident it can't get out, you're going to be okay with it being there, but you're not going to have a rattlesnake in your house, right? And I think the body is a similar way where it's there, it knows it's there, but it feels like it has protected it from any damage to the body. So what I show at the top of this slide is the current level of success. We have a wound, we put a material in it, uncontrolled binding, we encapsulate it, its body's fine with it being there, even though it's not really healed. And so I'd like to imagine a different world. Let's say instead, we have a wound, we take a biodegradable material that has controlled protein binding. Somehow that material knows how to put a specific protein in a specific way on that material. And then an even better step, it knows what cells to come and attract to it so it can start to heal the material. Let's say it's a bone, for instance, that you're trying to heal. It would then start to recruit osteoblasts to start the bone growth process. As time goes on, the bone starts growing. the material then starts to biodegrade, so that now the material is providing a scaffolding for the bone to grow into, but it's slowly going away, so that in the end, all of the material that you had initially is gone. Your body has grown all of the new material, and so you have no foreign material and a completely healed wound. This is an amazing future that I think that we can achieve. But what's keeping us from getting there? Very specifically, specific protein binding. We don't understand enough about how proteins interact with surfaces. And so now I've mentioned proteins several times, so we're going to have another poll. Get ready for it. So I'm going to launch the poll. Which of these is protein? We have tofu as A, we have B as rib steak, C is eggs, and D is a squiggly bunch of lines. So go ahead and answer. And don't put those keyboards away. We've got more polls coming. Got a few more coming in. We'll give you a few more seconds. All right, last call. Couple last stragglers. Okay. You guys, I knew this was a great audience. Let me share the results. So guess what? Everybody's right. So I worded the question really carefully of which of these is protein. Tofu is protein, rib steak's protein, eggs are protein. But if I had worded it, which of these is a protein, it would only be D that's the right answer. The other three are conglomerates of proteins, but the single protein is D, in fact, this squiggly bunch of lines. And so let's talk through a little bit about what a protein is. Okay. So a protein, at very simplest, is a chain of amino acids. This is something that we define as primary structure, and I showed the chemical structure of the amino acid on the screen. This can very much be thought of as a string of pearls. So each of the pearls represents an amino acid, and there are 20 naturally occurring amino acids. So the order of those amino acids or pearls on the string becomes very important for the protein's function. One of the reasons for that is that that order helps to define structure. And so there are four kinds of structure. Primary structure is the order of the beads. Secondary structure is how those beads order. And so I show that at the bottom of the screen with a twist in the pearl necklace. Or if you look at the protein, the red structure is known as an alpha helix, and the blue structure is known as a beta sheet. So those are secondary structures, and those are common structures that are seen in proteins. There's a higher order structure, which is called tertiary structure, which is where the bead necklace or the protein folds over on itself. And so you can see that in the pearl necklace here. You can see it in the protein, the way the red structure is folded over onto the blue structure. So that's known as tertiary structure. Now there's a fourth kind of structure that not all proteins have, and that's called quaternary structure. And it refers to multiple proteins interacting with each other. The protein I'm talking about today has quaternary structure. I wanted to put a game on here, but I didn't have enough time, but I'll point you to it. It's understanding how proteins fold, and it's really a video game, but it's also research. A person at the University of Washington, David Baker, wrote a program called Rosetta, which is one of the best programs for predicting structure to date. They made a game, being he and his students, made a game out of it to help people to learn how the rules about how proteins fold. And so it's a lot of fun. If you get if you are folding the structure right, you'll get fireworks, you get music, you get stars. It's just an amazing experience. And if you get them wrong, it gives you, kind of horn honks or something like that. So it's really interactive. It's a really instructive way to understand how proteins fold. Okay, so back to understanding how proteins bind to surfaces then. So now we understand what a protein is. How does that help us to understand how it binds to a surface? So I indicated before we want to be bio-inspired, and one of the first steps to that is understanding how biology does what it's trying to do. Enamel is this beautiful structure. I show a picture here of the intricate weaved nature that is what makes enamel so strong. Proteins are essential to the formation of this material, and they control the material's properties. And so if we understand how the protein interacts with this material, we can take those design principles and extrapolate those to other materials. And so we're going to talk about enamel and some of the proteins in enamel and how we're trying to understand that to then be inspired by them to do something else. Okay, next poll. Which of these materials is softest and weakest? Let me get the poll up. Launch polling. So you have a choice of steel, bone, enamel, or diamond. Give you a few more seconds to get your answers in. Last call, a few more. Okay, I'm going to end the polling. I'll share those results. Okay, so as it turns out, bone is the softest and the weakest material that I show here. What's really cool though is that enamel is as hard as steel and halfway as strong as steel, only half as weak as steel. It's an extremely strong material. The properties of enamel are incredibly complex to allow it to be this hard and this strong. I have kind of a funny story here. My husband is a mechanic and air conditioning is one of his specialties. And often he'll work for long haul truckers. And so one day it was a weekend, so I went with him to do an air conditioning job. And I was talking to the trucker, and he was asking me what I do. So I was telling him about my enamel research. And I said, yeah, enamel's as hard as steel. And he said, no, it's not. And I said, no, really it is. And he kind of grinned. He said, steel pipe did this, not as strong as steel. So it was pretty funny. I didn't talk about force or that kind of thing, but I just said, oh, okay, all right. So what we've been trying to understand is how proteins direct this amazing material to make something so hard and so strong. And we're doing that by approaching it in many different ways. So you can see the tooth and what that looks like if you, at a macroscopic level, when you just look at your tooth. But then you can blow that up with a really powerful microscope, and you see this amazing structure with this an interweaved pattern of very long and very thin crystals. If you expand that even more so that you're looking at individual atoms, what I'm showing here are the balls are the atoms in the surface material in the enamel, and the sticks are showing the protein binding to that surface. And what we'd like to understand is where each and every one of the atoms in the protein is relative to the atoms in the surface. And we're using some really advanced techniques to be able to understand and solve that. And so giving you just a comparison of bone and enamel. So I'm showing electron micrographs of enamel on top and bone on the bottom. These two micrographs are on about the same scale, and you can see that bones are very small plate-like crystals, whereas enamel are extremely long crystals. It's interesting that both of these materials are made of the exact same mineral, which is called calcium phosphate, but they have hugely different properties. Enamel crystals are 3,000 times longer than bone, and I was trying to think of a good way to think about how much longer this really is. And so here's Blitzen again. And so if you take Blitzen and you stretch him out 3,000 times longer than he will be as long as Everest is tall. That's amazing. And I've never seen a horse that's that long. But for some reason, nature decided to take the exact same mineral and in one case make it 3,000 times longer for a whole different purpose. And so the why nature does this is a very good question. And I think that part we can just use our intuition to understand, where your enamel is constantly being bombarded by all of the things we do to it. We put, pop in our mouth and sugar and juice and constantly chewing and changing the pH and constantly challenging our mouth and the material that's in our mouth, not to mention bacteria and all of the other things that are going in there. Whereas your bone's relatively protected from what I'll call the outside world. It really isn't exposed directly to it. And so your bones are constantly resorbed and remodeled while your enamel has to last a lifetime. And so I think the why is reasonably intuitive, but how nature does this starts to become a real challenge to understand. And so I'm going to start with a video courtesy of YouTube. It's about a minute and a half, and so enjoy, and I'll be right back.
Here the cells of the inner enamel epithelium differentiate into secretory ameloblasts. Ameloblasts are the cells that build enamel through this secretory process. These cells have a cytoplasmic extension on their distal ends called a Tomes process. Its sole function is to secrete enamel. This animation will focus on a small group of cells in order to examine the secretory process more precisely. Each ameloblast begins to secrete hydroxyapatite crystals from its Tomes process to create a layer of enamel. Crystals secreted from the proximal portion of the Tomes process are oriented perpendicularly to those secreted from the distal portion. This secretion pattern creates the rod-interrod formation of the enamel. The ameloblasts continue to secrete the hydroxyapatite crystals layer by layer. Because enamel is deposited incrementally, lines called the stria of Retzius are visible in the enamel. After the ameloblasts complete the deposition of enamel, they enter a maturation stage. The cells then secrete more minerals onto the enamel while absorbing most of its proteins. This process hardens the enamel further. The construction of enamel is now complete. This layer of enamel is the only one that will be created, and if properly cared for, will carry on through adulthood.
So I watched this video and I thought it's lies. It's all lies. And that wasn't completely accurate. Mostly just the research I do was all lies. But I was astonished that a time-honored institution like YouTube would let this sort of falsehood exist on the internet. And in case it doesn't come across in this medium, that was just dripping with sarcasm. So what I want to point out, that what the video described is that the hydroxyapatite crystals are inside the Tomes processes and they just get secreted out and off they go. And that is absolutely not what happens. We don't know what happens. What we know is that proteins are secreted out. There are calcium and phosphate ions that are there, and somehow the magic happens and those things are created into this beautiful and amazing structure that we get to take advantage of in our whole life. But the process of how this becomes this is very not understood. So just be careful what you watch on the internet or what you believe on the internet. Okay, and so if you look at proteins in developing enamel matrix, there are 4 of them. I'm showing 3 of them here. There's a methodology to remove proteins in animal models like mice or rats are most typically used. And by doing that, you can tell what the protein does. And so amelogenin is the most common protein in enamel formation. It's about 95% of the protein that's present. And when you grow a mouse in the absence of amelogenin, you see dentin, it's marked by the D. You see some enamel, it's a very thin, very brittle layer. And if you compare this structure to this structure, you can see they have almost nothing in common. There's no structure, it's very thin, extremely brittle, and it doesn't have that organization that true enamel has. The 2 other proteins, enamelin and ameloblastin, that are present don't actually grow a enamel layer if we remove those 2 proteins. And so all 3 of these are clearly very critical for enamel formation. We focus on amelogenin because it is such a predominant protein in enamel formation, and it's clear based on this animal model that it helps to control the structure of the formation to help us understand how it's interacting to control this material. And so overall, this is a very beautifully balanced system that is really easily disrupted. And our proposed mechanism is that protein structure is critical to how this mineral develops. And so that's what our research has focused on. A very reasonable question is, why don't we just add the enamel proteins into cavities to repair enamel? And it's very easily done. You can prepare these proteins in large quantities. You can put them in there, seal them in, and what happens? Well, many scientists have thought of the same thing. And you can see that the results, which are shown on the left side of your screen, don't match the results of enamel that's grown natively. You don't get the weaved pattern. You don't get the elongated crystals that are 3,000 times longer than bone. You get short crystals that don't have any structure associated with them. And so amelogenin is the protein that we're studying, and it's the one that causes this very thin layer of enamel. I'm showing the primary structure here. This is the beads on a string structure. I skipped the middle region. It's the region that generally I find less interesting, focused on the C-terminal region, the N-terminal, which is known to interact with other proteins, and then the other region, which is proposed to interact with hydroxyapatite. Now, I mentioned earlier that this protein has a quaternary structure, and that's when the multiple proteins interact. And so this is just a model of that. But when we started doing this research, there was really no clear understanding of when that nanosphere came to the surface. Did it stay a nanosphere or did it fall apart? What was the secondary structure and the tertiary structure of the protein in that nanosphere, and then when it was on the mineral? And in fact, I've got these questions all listed. Does the structure change from solution to when it's bound? What residues and regions are important to binding? And really important, there's a disease called amelogenesis imperfecta. I'll talk a little bit more about that later. That's a result of a mutation to the primary structure of amelogenin. How does the structure change there, which might give us some insight into what's happening when we see this malformed enamel? And so ultimately, we're trying to connect the structure of the protein to how the protein functions. One of the questions that we had was, is this quaternary structure that I showed you earlier what binds to the surface, or is it something else? So Jinhui Tao and Barb Tarasavich did some beautiful work that was really first of its kind for this field, using AFM to look at this protein on a hydroxyapatite crystal. Hydroxyapatite is the mineral that forms enamel. And what they found was, rather than seeing nanospheres on the surface, they actually see only smaller oligomers that are composed of several monomers, but not nearly as big as a nanosphere. And so it answered the question and was a very important result at the time. Prior to this, the common thinking in the field was that these nanospheres were the only functional form of amelogenin. This work was pretty definitive that more of the quaternary structures are important, from the monomer to oligomers all the way to nanospheres. So it was a really important result. One of the other questions that has actually been common in a lot of the biomineralization community, but that we were able to address, is the structure in solution predetermined to sit on the surface, or does it change when it goes to the surface? So Gary, June Shaw, and Rajith helped to provide some evidence here. What I'm showing here is a summary of NMR data, nuclear magnetic resonance data. And basically the thing to know is, the bigger this bar is, the bigger this delta C13 chemical shift is, the more structured the material. And you can see in solution, this is one of the carbons in the backbone of the protein. In solution are not very structured. These have a pretty small bar here. When we put this, though, onto the surface, these bars get really large, indicating that there's much more structure. We looked at a second set of carbons as well. This is a different carbon in the backbone of the protein. Again, not very structured in solution, but you go onto the solid and you see that it becomes quite structured. And so this is some of the first evidence that we have a structured material on the surface, and that it's quite floppy in solution. And in particular, though, understanding the structure on the surface was a real breakthrough. This is one melagenin. We used nuclear magnetic resonance, which is a characterization technique, to understand some of this structure. And then we collaborated with Dr. Jeff Gray and David Massica at Johns Hopkins University to use a computational technique to help to predict the rest of the structure. And so overall, this is a structure of an melagenin bound to hydroxyapatite. I'm going to skip that one. So one of the things I mentioned was something called amelogenesis imperfecta, which are mutations to amelogenin that cause malformed enamel. I show some examples of the enamel here, which can range from somewhat minor to very extreme. They can cause a lot of pain and often needs to be replaced at some point in your life. What's interesting about this is that it's a single amino acid that causes this. So there are two different types that I'll talk about. One causes hypoplasia, which is an underdevelopment of the enamel, and it's a single amino acid that converts to a different amino acid right here. A second type, it causes an overdevelopment of the enamel, and it's also due to a single amino acid. So you have 180 amino acids, you change one, and the whole thing falls apart. And so we wanted to understand if that was due to how it was interacting with the surface. And we had this theory that we might be able to understand this by using what I'm going to call a protein-eating protein, which is, it's an enzyme, but basically this enzyme comes and it chews up the protein that we're interested in. And what we thought we might be able to detect is changes in structure if it couldn't access that point where it eats the other protein. And I should point out, trypsin is the protein-eating protein that we chose. It has very specific sites that it can attack. And if it can't access those sites, then it doesn't break down. And so we used a technique that Jin Hui and Barb developed. And Jin Hui was really the person who developed this from scratch. It's in situ atomic force microscopy. And I'm going to play a couple movies here. And so I'll start the first one. This is the mutation that you saw on the left-hand side. And so let's start this movie. So what you're seeing is a protein binding to single crystal hydroxyapatite. So it's an enamel simulant. We've got protein binding. You can see it coming down to the surface. And we're going to add the protein-eating protein right here. And you can see all of that protein goes away almost instantly. So that in this case, the trypsin, or the protein-eating protein, had good access to that cleavage site. Now let's take a look at the second video. This is the mutation on the left, the T mutation. And so let's watch this one. So again, we see protein binding. Looks like it's binding about the same as the other one was binding. And so in a minute, we're going to add the trypsin, the protein-eating protein, and we're going to look for changes. So the trypsin's added. And you can see you're losing a little bit of protein, but nothing like the previous case where it really went away, almost like that. And so it's slowly going away, but it's clearly going away less quickly for this mutation than it did for the previous mutation. And so Jin Hui is able to quantitate this by using some image analysis software to count all of the individual molecules and then plot those into a plot. And I'm going to show that next. So we see this plot where there are 4 different proteins here. The green one was the first one, the blue one is the second one. And if you compare those to the naturally occurring protein, you can see the naturally occurring protein has much better access to that protein-eating protein site, where it's able to cleave it and remove it much more quickly than either of the 2 examples that I showed you. And so my question was, could there be a structural explanation? And so we're going to have our last poll now, so get ready. So the poll is, do you think the difference is a change in protein structure or protein binding? few more seconds. Okay, I'm going to go ahead and stop the poll. So we have a pretty equal guess as to which it is. And you know what? We guessed the same thing. Could be one, could be the other. Let's see if we can figure it out. So we looked at the structure in a couple of very specific areas in the protein. And what I'm showing on the screen right now may look very much to you like a painting that my mom saved for me from when I was 2. But in fact, to the trained eye, there are regions that you can look here to look for structural changes. So again, this is nuclear magnetic resonance. And in the circled region, you can see some places where there are green, red, and blue all overlapping. You see that on the left of the circle as well as on the right in the circle. And these are the 3 different proteins: the native protein, the protein with one type of mutation, and the protein with another type of mutation. What that says, because they're all overlapping, is that the structure really isn't changing that much in the particular areas that we looked at. However, what you also see is some places where there's only green and red, or only green and blue, not all 3 colors. What that tells us is that dynamics have changed. And that's a really important observation, because it says when that's coming down on the surface, it's wiggling around a lot more than what it used to. And that could be keeping the trypsin or the protein eating protein from being able to access that cleavage site. And so we still need to do more work here to understand it, but it does point to, in this case, more of a mobility than a structural argument. Okay, so we've done a lot of research. What does it all mean? So we had these fundamental questions we were coming in. Does the structure change when bound? Yes, it does. We've been able to very definitively show that it goes from something very floppy to something relatively ordered on the surface. What is the secondary, tertiary, and quaternary structure on the surface? We've started to provide some insight in there. We've shown that the quaternary structure breaks down to much smaller units, and we have some idea of what the secondary and tertiary structure are, but more work is needed to be done. The regions and residues that are important to binding are things that we're still trying to answer. I didn't talk a whole lot about that today. And then we also talked about the structural change as a function of mutation, and how, at least with the sites that we looked at, structure doesn't seem to be changing, but more, at least secondary structure, but more dynamics. And so taking that back to our dream of having something that we can ultimately put in the body that will allow us to fully biodegrade, we're starting to get closer. Understanding this protein structure in a natural material is going to help us to understand how we can control that protein structure when we get to other materials that we're working with. And then taking that back all the way to little nature, to trying to understand how all of those atomic and molecular level interactions work, to help us to understand how to ultimately make materials that can do what we want them to do. And with that, I'd like to thank the people that have done a lot of this work. I tried to indicate their pictures along the way, but fantastic group of scientists. I have had so much fun working with them. And also thanking the funders with EMSL and NIH. And I'm going to leave this survey up and turn it over to Megan.
Great, thank you, Wendy. We appreciate you taking time tonight discussing your research with everybody, and I know everybody appreciates it as well. We have almost 70 people joining us tonight, so we'll go ahead and jump right in. They do have some questions for you. So our first question is protein folding a response to charge concentrations in the molecule?
Absolutely, yeah. In fact, not only charge, but also a property called hydrophobicity is important, where there's not charge. And because proteins are in water, it's trying to protect that not charged region from water. So often the folding is driven by trying to protect this hydrophobic core from water.
Great, thank you. And you also mentioned XPS as a characterization technique. What did you use XPS for? And maybe you can refresh everybody what XPS is as well.
That must have been on an early slide. So we used XPS way back, X-ray photoelectron spectroscopy. And this was probably 15 years ago when we were trying to look at the thickness of the protein layer. And so you can XPS kind of shoots at the layer at the surface and bounces off, and you can look at the surface interface and what's there. And so that would have been a long time ago and isn't something we're actively using.
And you showed the results of the NMR. What are we seeing when we're looking at those NMR results?
That's a great question. So with NMR, it's an amazingly specific technique. So it can tell you a particular, it's called a nuclei of carbon is most common, and it's what I was showing, where you're looking at individual carbons. And if you have really good resolution, you can actually see each and every individual carbon in a particular molecule. In our samples, they're very complex. There are a lot of molecules. There are a lot of pieces of the molecules. There are a lot of carbons. So you start to get overlap. And so in some of those, the watercolor plots that looked like a painting from when I was 2, they're in 2 dimensions, and that helps extrapolate it into the second dimension so that you can help to provide some additional resolution. But basically what you're looking at is each and every individual carbon atom in the molecule.
Great, thank you. One question, our next question is, I was given the antibiotic tetracycline at an age when my permanent teeth were forming. Somehow the tetracycline caused my teeth to be permanently stained. How can a chemical in the bloodstream participate in such a process? And why would tetracycline participate but not other molecules?
Wow, that's a really great question. I can safely say I don't have a great answer. I can speculate though. So it likely, as we saw in the movie that has lots of lies in it, that the myeloblasts probably absorbed some of that chemical, the tetracycline, and my guess is that got impregnated into the calcium phosphate. So the calcium phosphate is a structure that has a very specific orientation of atoms. If this organic molecule was inserted into that, similar to how a protein might be inserted into that, it wouldn't be able to leave, and that prevented the enamel from being able to harden or finish as easily as it would have otherwise. And so that would be my guess as to what happened there.
Thank you. What are some of the most exciting developments you've seen in bio?
Are you done?
I am.
Okay. So 2 of the really exciting things I've seen. One is a study where they took a petri dish, not a petri dish, they took a Teflon plate, they carved a notch in that Teflon plate, and they put heart cells in it. They let the heart cells grow and develop. As the heart cells got close, within a certain proximity of each other, they started beating on their own, which I just found fascinating, that there's some sort of sensing between them that enabled them to start to beat. To me, that was just a really very cool study and has a lot of implications for potentially, heart replacements very, very far down the road. Another one was a study where they developed the bone structure of a finger. So they took a mouse and they put a softer piece of plastic for the long finger, and they took a harder piece of plastic for the joint, and they grew this bone, and they were both biodegradable, grew this bone in a mouse, and the material, they put stem cells on it. They were able to grow these bones to look like the structure of a finger, and in the end, all of the plastic was completely degraded. So that was a really cool study that shows that we're on our way to really being able to implement some of these changes.
Great, thank you. What are some of the biggest challenges besides controlled protein binding?
Let's see. I think one of the biggest challenges is something called vascularization. So if you look at your skin or your bone, you have blood vessels and arteries running to bring blood and nutrients out to those materials. That's been one of the harder things to control, is how to intentionally put the vascularization material alongside bones, for instance, to make sure that you're getting all of the food and the nutrients out to the minerals once you develop them.
Okay, and we have one final question for tonight. How can one amino acid make such a big difference in how a protein works?
Oh, that's also a great question. And it's one of those questions that structural biologists would really like to understand. But it really points to that dependence on that pearl string, the string of pearls, that dependence on the order of those amino acids is so important to function. And I guess to answer the question specifically, if you change one of those amino acids, you could change the charge or the hydrophobicity, and that changes how it folds. And that change in folding can reveal a certain part of the protein or hide a certain part of the protein that before was doing a specific function. So by changing that, it can have a huge influence. Now, something that should be pointed out is that there are proteins that you can change single amino acids and it really doesn't affect it. And so there are specific places in some proteins that really matter and that really changes function.
Wonderful. Well, thank you, Wendy. We really appreciate you taking time to present your research to the community. And thank you to all of you who attended tonight's seminar. Again, I'd like to remind everyone one last time to take our brief survey. At the end of the survey, you can also sign up to receive notifications about our future seminars, including our special 5-part COVID series taking place every Tuesday in March. So again, thank you so much to everyone who joined us tonight. We'll hope to see you in March. Have a great evening.
Thanks, Megan. Thanks, everyone.